You all have read about the Earth's crust and the layers that make up the crust, right? The elements present in the Earth's crust are called rare earth metals, which include many metals of the lanthanoid and actinoids family. As you can see, the elements from the F block consist of two series, lanthanides and actinides, which we will be discussing in this session. As you can see here, the atoms of lanthanoid elements have an electronic configuration with 6s2 in common and variable occupancy of 4f11. The electronic configuration of the tri-positive ions are of 4Fn, where n varies from 1 to 14. Now, if you see the atomic and ionic radii decreases from lanthanum to lutetium, which is also called lanthanide contraction. The contraction is similar to that of the transition series, which happens because of the imperfect shielding of one electron by another in the same subshell. Now, if you see two elements, zirconium and hafnium, zirconium belongs to the 4D series and hafnium belongs to the 5D series. They have similar chemical properties. Thus, they are difficult to separate. This is due to the fact that they have similar atomic radii due to lanthanide contraction. Next, the oxidation state of all lanthanide elements is +3. Some metals formerly have +2 oxidation states. A few lanthanide metals exhibit +4 oxidation states on rare occasions. The oxidation state of lanthanides is affected by the stability of the F subshell in such a way that +4 oxidation state of cerium is preferred because it acquires a noble gas configuration. But it reverts to a +3 oxidation state. Thus, it acts as a strong oxidant and can even oxidize water, though the reaction is slow. Whereas, in the case of europium, it shows +2 oxidation state because of the half-filled 4F configuration, as you can see here. However, one thing to note here is that europium 2+ is a strong reducing agent by changing it to the common +3 oxidation state. Similarly, in ytterbium, Yb2+, which has F14 configuration, is also acting as a reductant. And praseodymium, neodymium, terbium, and dysprosium also exhibit +4 state, but only in the case of its oxides. Let's now focus on physical properties of lanthanoids. All the lanthanoids are silvery white soft metals and tarnish rapidly in the air. The hardness of the lanthanoids increases with increase in the atomic number. The melting point range between 1000 Kelvin to 1200 Kelvin, but samarium melts at 1623 Kelvin. Lanthanides are good conductors of heat and electricity. Now, if you see the chemical properties of lanthanoids, they liberate hydrogen from dilute acids and burn in halogen to form halides. Metal combines with hydrogen when gently heated in the gas. Just like alkali and alkaline earth metals, lanthanides and actinides also form oxides and hydroxides. The carbides are formed when the metals are heated with carbon. Lanthanides, because of their unique properties, are also used to make alloys. For example, mish metal, it contains 95% of lanthanide and 5% of iron. Also, metal oxides of lanthanides are employed as catalysts in petroleum cracking. Now, let's discuss about actinoids. Actinoid series have 15 consecutive chemical elements in the periodic table from actinium to laurentium. Actinoids have the electronic configuration of 7s2 and variable occupancy of the 5f and 6d subshells. Only thorium and uranium occur naturally present in the Earth's crust. Rest all are prepared with nuclear processes. Now, if you see the ionic sizes of actinoids, there is a gradual decrease in the size of atoms or metal oxide ions across the series, as represented here. This is known as actinoid contraction. The contraction is greater from element to element in this series, resulting from the poor shielding by 5f electrons. On the other hand, the distribution of the oxidation states is very uneven. The elements in the first half of the series frequently exhibit higher oxidation states. The oxidation state increases from +4 in thorium to +5, +6 and +7 respectively in proactinium, uranium and neptunium respectively, but decreases when it comes to the succeeding elements. Moreover, if you see the physical properties of actinoids, all the actinoids are soft and metallic in nature and show radioactivity. They have several crystalline structures. They all ignite spontaneously in air, and that's why they are pyrophoric in nature. Most of the trivalent actinides have a striking color in aqueous solutions. The variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electrons is roughly parallel to the corresponding results for the lanthanoids. The latter have higher values though. In case of chemical properties, actinoids have lower ionization energy and that's why they are more electropositive in nature than the corresponding lanthanoids. They react with hot water and oxygen gas in air. They are strong reducing agents. Now, let us learn some of the uses of actinoids of which we are unaware. Thorium, placed in actinoid series, possesses high temperature and high pressure resistance, and it is used as an ideal insulator. It is also used in many smoke detectors and treatment of cancer. On the other hand, plutonium is used as a fuel in many space aircraft. There are many useful applications of the D and F block elements and their compounds. Notable among them being in varieties of steels, catalysts, complexes, organic synthesis, etc. Stay tuned for the next session to discuss some of the important applications of these elements. With this, let's summarize this class.
Manorama Horizon, learning made simple.